Yeah, I will talk about our latest results in terms of Lightfield Media Production Systems. I'm from Fraunhofer IIS in Erlangen, Germany, and I'm heading the group Computational Imaging and Algorithms there. So this is a short overview about this talk. I will show you how we capture light fields with our camera arrays. I will show you which visual effects for movie productions can be enabled by the technology, and then I will show you the first short movie light field production called Coming Home, which we produced jointly with Stuttgart Media University last year. So when you capture light fields, there are different systems which you can use. You can use micro-lens array-based cameras, such as from Raytrix. You can use camera arrays. This is our approach here in this presentation. Or you can use multi-aperture cameras which do not have a main optic. There are some emerging cameras from this field as well. But today we will use these camera arrays. So the reason is, for movie production you want to have high resolution per camera, and however you have of course some new challenges, such as you need many cameras. In theory you need a very dense sampling, and so the cameras need to be small and still good, and so on, and the amount of data you capture is of course also high. So generally speaking, there's this triangle with contradictory goals about camera arrays. You can have viewpoint flexibility, image quality, or efficient storage and resources, but not all at the same time. You can have a large array with lots of cameras, so you can really change your viewpoint dramatically, and you have a nice image quality because you have a dense sampling, but storage and resources are really a downside. Or you can go for a small array, say dense sampling still, but the viewpoint flexibility somehow lags. Or you go to some kind of sparse array where you say, okay, I want to have that viewpoint flexibility and only a limited number of cameras, but then view interpolation becomes harder, so it might impair the image quality. So this is just as a general speaking when you want to acquire light fields with camera arrays. So you have to adapt this usually to your dedicated application. So here for a production we did 2 years ago, which we processed last year, we used an array with 16 cameras, and to try out our processing chain. And at that time we were not able to capture videos. This is why we decided to do a stop-motion production and test all this chain in the first step. So we set up a plot for a small short movie, and had a scene set up, camera set up, did the shooting, and then the post-production. I will show you some pictures about this. This is our studio in Erlangen. And here in the corner, we set up the scene for the stop-motion production. Here's a 16 camera array, 4x4 cameras, some lighting, some background. This is in a little bit more detail. This was shot before Lego the movie came out. Yeah, so we claim somehow to be the inventors of nowadays Lego stop-motion. So here you see that person, which will be animated manually by a student from a film university. And so there is a clip, there are more frames, but this is captured by all 16 cameras, so you get the same clip captured by 16 cameras. And now starts the image processing. It's about, first step, what we have to do is rectification. So of course we did some rough alignment of the cameras, but you want to have a very precise per pixel alignment such that the corresponding pixels are in the same image row, and in the same image column at the same time in order to ease the further processing, yes? So that you can apply stereo depth estimation here and stereo depth estimation there and easily combine the disparity maps. So we have a dedicated multi-camera rectification algorithm for that, which does this equalization. Then, well, it's only about finding the correspondences which generate you depths or disparity maps in the first step, which can be filtered and filtered to enhance the quality using algorithms as proposed by Atanas and Martin and colleagues. And so at the end, you can do some 3D reconstruction if you want. This is usually what we do not need for depth image-based rendering. We do not need a point cloud, but if you want, you can generate one. So this is a colored version of the disparity map, which we generate per frame and per view. Yes. So once you have that data, what effects can you apply? So you can move the camera in X direction, Y direction, Z direction. So you can do some free viewpoint rendering, basically limited to the size of the array, but also going in Z direction, because you can combine the light rays according to light field rendering. So, and for post-production, there are effects such as vertigo effect or dolly zoom effect, matrix effect. You can create stereo pairs at arbitrary interaxial distance, and you can reposition the depth of field. And we will see how this can be managed. So we created plugins around our algorithms, which can be used here, for instance, with an CIVIT Media Composer. And so it's a very, very natural way to use it for people in post-production. So you basically place the filter, and now here you can have a filter where you change the position in X. And here, over the time, the camera moves with the video in X direction, yes? So you have set some keyframes, and here in the timeline, you can go back and forth. And the parameters for the keyframes tell the plugins how far you want to move the camera, for instance. Or you can change the position of the camera in X direction. This is what we have seen right now. In Y direction, I'm sorry for the lower resolution. This is due to this VGA. You can see this really with parallax. You can see how it moves. And also in Z direction. Also, we have captured an X and Y array. You can move it in Z direction because you have the full light reconstructed using the geometry data which you acquired using disparity generation. And you can also change the focus from background to foreground or vice versa. Yes. And so there's one little thing. I promised the vertigo effect. So when you combine a virtual dolly with a virtual zoom or digital zoom, then you get a dolly zoom. And you can parameterize this. And you get here this vertigo effect for stop motion data, which is, well, quite difficult to achieve using traditional approaches. And yeah, we can do this also not only in CIVIT Media Composer, but also in the Foundry's Nuke. And if we do the final rendering, this looks like this. So here we have a virtual movement of the camera. So the array was fully static at the time of shooting. And here the camera moves from top left to bottom right, and then to the left. And we pull the focus from the background to the foreground. And yeah, this is something what we can achieve. So now let me come to the latest production. This was about creating a short movie with a real actor, not a miniaturized scene like for the Lego. And we wanted to find out, how far can we go right now, and not only in 10 years, but is there a valuable use case and scenario for using Lightfield in today's production? And So we had lots of meetings with experts and brainstormings, and so we tried a special setup with one hero camera, here a Sony F3, a half-transparent mirror as known from stereoscopic 3D, and behind a 3x3 Basler array. So this is how the rig looks like without the mirror box. So here you have this cinema quality camera, and here you have the 3x3 array. And as I said, we did this together with Stuttgart Media University, in Stuttgart. Here another making of picture. Here you see this with the mirror box. And the idea was really to get the best of both worlds, like having a high quality camera so that you can guarantee that you have at least one high quality 2D image. And if everything works fine with the algorithms, you can have a good depth map in addition also for the hero camera, or do some fancy Lightfield stuff. So here, this was a virtual, well, the set, and here was the actor, and this was like a 70s hotel room with some actor doing some stuff. Here you see it can be perfectly mounted on a dolly, like you would do it for a 3D rig. And so it can be operated quite normally. This is the actor. And I will skip that due to time restriction. I will show you how the node-based Lightfield post-production looks like. So we have captured that content now. In the first step, we said we want to integrate it into existing post-production pipelines. So, and this shall be used by non-experts or not computer vision experts. So we need an easy way to process the data. And this starts obviously with the import of the data. So we wrote a dedicated plugin for importing multi-camera data. And just to give you an idea about how it can look like. So we say center camera is hero camera. We have a 3x3 array. You browse to the folder. This is which is also expected to be done by post-production creatives. And now the import process is automated. So you have all 9 views here. They can be joined. You can toggle through the views. And so now everything works in this node-based workflow. This is the first step. In the next step, you apply geometric corrections. Basically, this is applying the rectification, which I have shown earlier. So you get here the footage, the uncorrected footage, and after correction, all pixels are in the same image row or image column. Then you do some disparity estimation. And you will do this as well with a plug-in for the post-production software. And you can see everything in the graphical user interface. So here you have your joint views. You just grab a new plug-in. You say, OK, I have that 3x3 geometry as well. You can set up some metadata. You just connect it to the joint views. And then the disparity estimation process is just started automatically. And it creates disparity maps here now in the alpha channel. And these are the raw disparity maps as it comes from a block matcher. And they will be filtered in different steps. And depending on how much time you have, they get better and better. And you can, again, use all this sophisticated algorithms developed by the partners here in the network. And at the end, you will hopefully get some decent disparity maps. And, well, now what can you do with the disparity maps? Disparity maps are not perfect, yes. And the question is, are there use cases where you can achieve something useful already with non-perfect depth maps? And so we tried different use cases, and one was depth-based color grading. And in depth-based color grading, this is a very forgiving approach. Here in the background, we will change the color temperature or the luminance without changing it for the foreground. And yes, the disparity maps might have some bleeding pixels here, but you will not see it in the result. Yeah? So this application is totally forgiving for such an approach. You can see it again. Pre-grade. And now in the background, you're going to change it. You can render virtual cameras. I will show something, another result on this later for more the free viewpoint video. But again, this is another plugin which you connect to the view, and you can also connect from outside the camera tracker inside Nuke, which tells the plugin where to render that virtual camera at. So if you had a camera tracker in before, like 3D equalizer or PF track, this can be combined. You can do focus pulling in post-production. So again, here this is applied virtual bokeh to this footage. That's known from Lightfield cameras that this is possible. You can do some depth space compositing, and here the depth space were not yet perfect. So you see that non-perfect depth map is a little bit noisy. We created a mask out of it, and now we use this instead of green screen for object segmentation. This is not this part of the sequence, but which the part will come now. We put another background in front of this foreground. This was a use case where you can see if your depth maps are not perfect, that segmentation is not so forgiving. That's a learning. But there was something else, and this came out in this brainstorming with the students and the experts. It's about relighting. So once you have the depth maps, you can create normal maps. And when you have normal maps, you can apply workflows which are known from CG, and to reposition virtual light sources. So here this is inside Nuke again. You can add a light source, a virtual light source, to this footage, and now reposition that light source and make it, for instance, turn around her head. Yes? And if you do that, you get a rendering which is at least a very good start, I would say. So here you can see how the light source is rotating around her head. It works quite fine if the light source comes from the front. If it comes from the background, you'll see some segmentation maybe. But at least if you have some reasonable light source, it works very fine. And to underline this, here we added a light source to an existing one. So here the actor is lighting a match, and we wanted to improve the luminance, the brightness of that flame, of that little flame. So we tracked in the video the position of that match, added the virtual light source, and created some added light. So it changes the lighting situation not dramatically. And this is totally forgiving, and you will not see any artifact. So you have, of course, reflections by his body and his hand. And so this is the light which you add. And this can be also done totally interactive and seamlessly integrates into your post-production workflow. You can do also a combined relighting with CG and real content. So this is a CG teapot. This is a real background in the real table, and you can do some rendering, and then you will see that there's a combined relighting which can enhance the realism, and is also interesting for augmented reality applications. Okay, now I would like to show you this video. I hope I have some sound. Show you which effect was applied to each scene, yes? So you can see which camera was used it's basically always the camera array, except in the first scene where it was.
It's a tough routine.
Yeah.
You go to your limits for the job. So you pretend to be a violinist. You don't wear your own clothes. Your credo, pretending, is everything. If they bust you, you're out. So you go to the opera as a fake musician, but not into the orchestra pit. You go to the toilet and wait. There's the target. Perfect view. Pull and fire. A glance over the shoulder. Was there anyone? Did anybody see you? You never know. It's an occupational hazard. One mistake and you're gone. The nerves should be blank, really. But you keep it calm when you drink Meliston tea. The tea for relaxed routine. Meliston tea. Drink tea, calm down.
Yeah, this was the short movie, and I think I'm done here. Just one thing, because yesterday Atanas mentioned it. So he showed some picture, and I did a picture. Oh, sorry, just 10 seconds. And I did a picture of the DeLorean. Yes, it is expected today at 4 p.m. 29 in LA. They have built up, as they are waiting for the DeLorean to arrive. And so this is from Back to the Future. And well, maybe it comes today, yeah? We are not sure yet, but cameras are observing the street in LA, so let's have a look, yeah? So thank you very much for your time.
Thank you.